Arumugalakshmi from Sri Jaindra Saraswati Vidyalaya Matriculation High Secondary School, Singanallur. Namaste. Today we are going to discuss the problems in ray optics of class 12 physics. First problem. An object of 4 cm height is placed at 6 cm in front of a concave mirror of radius of curvature 24 cm. Find the position, height, magnification and nature of image. So first we will start with the given. The height of the object is given as 4 cm. The image distance we have to find. So the object distance is given as 6 cm. We apply our sign convention. Hence u is equal to minus 6 cm. The radius of curvature r is equal to 24 cm. We are supposed to find the height of the image, the magnification and the image distance. So these things we have to find. So we will start the solution with the relation between focal length and radius of curvature, which is f is equal to r by 2. Substituting the r value, we get the f value as 24 divided by 2, which is equal to 12 cm. Now we substitute this f value and u value in the mirror equation, and from the mirror equation we will find the v value. So the mirror equation is 1 by f is equal to 1 by v plus 1 by u. Now substituting the values of f and u in this equation, we get minus 1 by 12 is equal to 1 by v minus 1 by 6. Hence 1 by v is equal to minus 1 by 12 plus 1 by 6. Now here we will take LCM and we will find 1 by v is equal to minus 1 plus 2 the whole divided by 12, which implies 1 by v is equal to 1 by 12. Hence v is equal to 12 cm. So the image distance is found as 12 cm. Next we have to find the magnification. So magnification, we know the formula as minus v by u. Substituting the v and u value, we get minus 12 divided by minus 6, which is equal to 2. So the magnification is equal to 2. Next we have to find the height of the image. For magnification, we know the another one formula as height of the image divided by height of the object. So here substituting the magnification value and height of the object value, we can find the height of the image value, where hi is equal to 2 into h naught. So hi is equal to 2 into 4, which is equal to 8 cm. So we have found the image distance as 12 cm, the magnification as 2 and the height of the image as 8 cm. Now the second problem. An object is placed in front of a concave mirror of focal length 20 cm. The image is formed is 3 times the size of the object. Calculate the two possible distances of the object from the mirror. So here the data given is the focal length is minus 20 cm because of sign convention. The image distance is 3 times the size of the object. So v is equal to 3u. It might be plus or minus. So we will get two possible distances of u with plus 3 and minus 3. So we will have two possible answers for this question. So first we will move on with v is equal to plus 3u. So once again we start the problem with the mirror equation, which is 1 by f is equal to 1 by v plus 1 by u. Substituting the f value, v value from the given data, we get minus 1 by 20 is equal to 1 by 3u plus 1 by u. Here we will take 1 by u as common outside in the RHS. Hence minus 1 by 20 is equal to 1 by u into 1 by 3 plus 1, which is nothing but 4 by 3. So minus 1 by 20 is equal to 1 by u into 4 by 3. Hence, u is equal to minus 20 into 4 by 3, which is equal to minus 80 by 3 centimeter. This is the first u value. The next value is, for the next value, we substitute v value as minus 3u. Once again, we start from the mirror equation, which is 1 by f is equal to 1 by v plus 1 by u. Here, we substitute the f value and v value from the given data. We get minus 1 by 20 is equal to minus 1 by 3u plus 1 by u. Here, once again, we take 1 by u as common. So, we get minus 1 by 20 is equal to 1 by u into minus 1 by 3 plus 1, which is nothing but 2 by 3. Hence, minus 1 by 20 is equal to 1 by u into 2 by 3. From this equation, we get u is equal to minus 20 into 2 by 3, which is nothing but minus 40 by 3 centimeter. Hence, we got two object distance, which is minus 80 by 3 centimeter and minus 40 by 3 centimeter. The third problem. A beam of light consisting of red, green and blue is incident on a right-angled prism. The refractive index of the material of the prism for the above red, green and blue colors are 1.39, 1.44 and 1.47 respectively. What are the colors suffer total internal reflection? So the given data are the refractive index for red is given as 1.39, for green is given as 1.44 and for blue is given as 1.47. We are supposed to find the colors which suffer the total internal reflection. So first let us find the refractive index of the given prism using the formula n is equal to 1 by sin IC. So n is equal to 1 by IC value is 45 degrees. So 1 by sin 45, which is equal to 1 divided by sin 45 is 1 by root 2. So 1 divided by 1 divided by root 2 will become root 2. So the refractive index is equal to root 2, which is nothing but 1.414. So the colors whose refractive index is greater than 1.414 will suffer total internal reflection. So from the given data, green and blue whose refractive index are 1.44 and 1.47, which are greater than 1.414, will suffer total internal reflection. The fourth problem. An object is placed at a certain distance from a convex lens of focal length 20 cm. Find the object distance if the image obtained is magnified 4 times. So the given data is focal length is equal to 20 cm and the magnification is equal to 4. And we are supposed to find the object distance. So we start the solution using the lens formula, which is 1 by v minus 1 by u is equal to 1 by f. Now substitute the value for m is equal to 4. Since m is equal to 4, m is nothing but v by u. Hence v is equal to 4 times u. So in the lens equation, instead of v, we are going to substitute 4u. So the equation becomes 1 divided by 4u minus 1 by u is equal to 1 by 20. Hence 1 by 4u minus 1 by u is equal to 1 by 20. Here once again we take 1 by u as common. Hence 1 by u into 1 by 4 minus 1 is equal to 1 by 20. So here once again you take LCM and you find 1 minus 4 by 4, which is nothing but minus 3 by 4. Hence 1 by u into minus 3 by 4 is equal to 1 by 20. Hence simplifying, u is equal to 20 into minus 3 by 4, which is equal to 5 into minus 3. Hence u is equal to minus 15 centimeter. The answer is the object distance is minus 15 centimeter. Fifth problem. Obtain the lens maker's formula for a lens of refractive index N2 which is separating two media of refractive indices N1 and N3 on the left and right respectively. We start the solution using the general formula for refraction of single spherical lens which is given by N2 by V minus N1 by U is equal to N2 minus N1 divided by R. This is the general formula. This formula we are going to apply for first refraction and second refraction. First refraction is from N1 to N2. Second refraction is from N2 to N3. So this we are going to apply for first refraction. So the equation becomes N2 by V. V is the image distance. For first refraction, the image distance is V1. Hence, N2 by V1 minus N1 by U. Object distance remains the same. So, N2 by V1 minus N1 by U is equal to N2 minus N1 divided by R1. This is the equation for first refraction. Now for the second refraction. Second refraction is from N2 to N3. Hence, we have N2 by image distance is V. So, N3 by V minus N2 divided by the object distance will be V1 which is equal to N3 minus N2 because here the refraction is from N2 to N3. Hence, it is N3 minus N2 divided by R2. So this is the equation for second refraction. Now we add equation 1 and 2. So when you add equation 1 and 2, we get N3 by V minus N1 by U is equal to N2 minus N1 divided by R1 plus N3 minus N2 divided by R2, where the expression N2 by V1 and minus N2 by V1 will get cancelled. So we are writing the remaining terms. When you write the remaining terms, we get the answer as N3 by V minus N1 by U is equal to N2 minus N1 divided by R1 plus N3 minus N2 divided by R2. So this is the expression for the refraction of single spherical lens with the two refractive indices. The sixth problem. A thin converging lens of refractive index 1.5 has a power of plus 5 diopter. When this lens is immersed in liquid of refractive index n, it acts as a divergent lens of focal length 100 cm. What must be the value of n? So, here this problem consists of two parts. In the first part, you have got a convex lens whose refractive index is 1.5 and whose power is 5 diopter. Here the light ray is passing from air to the lens. Hence N1, which is the refractive index of air, is 1. N2 is the refractive index of the lens, which is 1.5, and the power is 5 diopter. After this lens is placed inside a liquid. So when it is placed inside a liquid, it behaves as a divergent lens. Divergent lens means it behaves as a concave lens. So when it is kept in a concave lens, its focal length is given as f is equal to 100 cm. And we are supposed to find the refractive index of the liquid. So we will start the derivation with the first part. So in part 1, the convex lens, the power is given as 5 diopter, N2 is 1.5 and N1, which is the refractive index of air, is 1. So using the power first, we are calculating the focal length using the formula f is equal to 1 by p. So which is equal to 1 by 5, which is nothing but 0.2 meter, which can be written as 20 centimeter. So the focal length of the convex lens is 20 centimeter. In part 2, this convex lens, when placed inside a liquid, it behaves as a concave lens. So for that concave lens, the focal length is given as 100 centimeter. So f is equal to 100 centimeter. So next we will move on to the problem starting from the lens maker's formula, which is 1 by f is equal to n2 by n1 minus 1 into 1 by r1 minus 1 by r2. So for air, first the light ray is passing from air inside the convex lens. So the lens maker's formula for part 1 is 1 by f. F is 20 centimeters. So 1 by 20 is equal to 1.5, which is N2, divided by 1, which is air. Hence N1 is equal to 1.5 divided by 1 minus 1 into R1, R2 values we don't know. So we will have that as it is. 1 by R1 minus 1 by R2. This is for the first part where the light ray is passing from air to convex lens. Now for the liquid. So for the liquid, the lens maker's formula for part 2 is 1 by f. Here the f we have to include the focal length of concave lens, which is 100. Hence since it is a concave lens, we use the negative sign. 1 by minus 100 is equal to 1.5 divided by n value we do not know. The refractive index of liquid we do not know. Hence we have it as n. Hence 1.5 divided by n minus 1 into 1 by r1 minus 1 by r2. Now we have to divide equation 1 by 2. We get, dividing equation 1 by 2, we get 1 by 20 divided by 1 by minus 100 is equal to 0.5 divided by 1.5 divided by n minus 1. Here, dividing the LHS, we get minus 100 divided by 20 is equal to 0.5 divided by 1.5 divided by n, the whole minus 1. Now, here in the RHS, we have got in the denominator 1.5 divided by n minus 1. This we are taking to the LHS. Hence, it becomes 100 divided by 20 is 5. Hence, minus 5 into 1.5 divided by n minus 1 is equal to 0.5. Now, this 5 which is outside the bracket in LHS, we are taking that inside the bracket. Hence, 5 into 1.5 minus n divided by n is equal to 0.5. Now, when you multiply 5 inside, we get 5 into 1.5, which is nothing but 7.5. So, minus 7.5 plus 5n is equal to 0.5n. Once again, we bring the n terms on one side. Hence, 5n minus 0.5n is equal to the number 7.5. We take it to the RHS. Hence, 5n minus 0.5n is equal to 7.5. 5 minus 0.5, which is nothing but 4.5. N is equal to 7.5. Hence, n is equal to 7.5 divided by 4.5, which is nothing but 75 divided by 45, which is nothing but 5 by 3. Hence, the refractive index of the liquid is 5 divided by 3. Seventh problem. If the distance d between an object and the screen is greater than 4 times the focal length f of a convex lens, then there are two positions for which the lens forms an enlarged image and a diminished image respectively. This method is called as conjugate foci method. If d is the distance between two positions of the lens, obtain the equation of focal length of the convex lens. So here we have to find the focal length of convex lens. The distance between the object and the image of the first lens is u1 and v1, which is capital D. Capital D is the distance between the image and the object of the first lens, which is 1. Hence, D is equal to u1 plus v1. From this equation, you can get the value of v1 as D minus u1. This we will be substituting in our lens equation. Hence, we use our lens equation, which is 1 by v minus 1 by u is equal to 1 by f. Here, instead of v, we are going to substitute d minus u1. Hence, the equation becomes 1 by d minus u1 minus 1 by minus u1 is equal to 1 by f. In the LHS, we We simplify the LHS using the LCM method. Hence, minus u1 minus d minus u1 the whole divided by minus u1 into d minus u1 is equal to 1 by f. Our simple LCM only we are using in the LHS. After that, this minus u1 and inside if you take the minus inside it becomes plus u1. Outside you have got minus u1, inside it is plus u1. So they will get cancelled and in the LHS you get minus d divided by minus u1 into d minus u1 is equal to 1 by f. Now, in the above equation, we are going to do cross multiplication. Hence, we get minus df is equal to minus u1d plus u1 square. Now, you bring minus df to the RHS and you make one quadratic equation. The equation is u1 square minus u1d plus df is equal to 0. This equation resembles a quadratic equation which is x is equal to minus b plus or minus square root of b squared minus 4ac divided by 2a. This is the solution for the general quadratic equation. Here in our equation, the value of x is u1, the value of a is 1, the value of b is minus d, the value of c is d into f. Hence, substituting in the general solution, we get u1 is equal to d plus square root of d squared minus 4df divided by 2 and u2 is equal to minus d minus root of d square minus 4df the whole divided by 2. So you get both the values plus or minus. Plus value I am assigning to u1, minus value I am assigning to u2. So we get two values of object distance which is u1 and u2. The distance d, small d is the distance between u1 and u2. So now what I am doing is I am subtracting u1 minus u2. Just substitute the u1 u2 value here. You get d plus square root of d square minus 4df divided by 2 minus d minus square root of d square minus 4df divided by 2. Here the first term d and minus d get cancelled. Hence you have 2 into square root of d square minus 4df divided by 2. So numerator 1d you have, denominator 1d you have. So both will get cancelled and you will get the d value as small d is equal to square root of d square minus 4df. Now square the above equation. You get d squared is equal to capital D square minus 4df. Our aim is to find the expression for focal length. So you take 4df to the LHS. Hence the equation becomes 4df is equal to d square minus d square. Hence f is equal to d square minus d square divided by 4d. So the final expression for focal length is f is equal to d square minus small d square divided by 4d. This is the expression for focal length for conjugate foci method. Eighth problem. Prove that a convex lens can only form a virtual erect diminished image. This is a very simple one. So we will start the solution with the first diagram. See, in the first diagram, the position of object is at infinity. We know that when the object is at infinity, you get the image at focus. So the position of the image is focus. Now when you see the diagram itself, you will understand that the size of the image is point size. It is highly diminished. And the nature of the image is virtual. From the diagram itself, we will understand that the nature of the image is virtual. This is for the first case. In second case, anywhere before infinity, you can keep the object. Hence, the position of the object is anywhere before infinity. Hence, the position of the image will be between focus and the pole. And the size of the image will be diminished and the nature of the image will be virtual. So, from this above two illustration itself, we can understand that a convex lens can only form a virtual, erect and a diminished image. Ninth problem. A point object is placed at 20 cm from a thin plano-convex lens of focal length 15 cm whose plane surface is silvered. Locate the position and nature of the final image. Here the given data is object distance u is equal to 20 cm, focal length is equal to 15 cm. We are supposed to find the position of the image, that is the image distance we have to find. First thing what you have to understand is a silvered, that is a plano-convex lens which is silvered, is a combination of a lens and a mirror. Hence, the focal length will be a combination of lens and the mirror also. Hence, when you find the power, you have to include three terms. That is, first, when the light ray enters from air to lens, you will have one refraction. After that, from lens to mirror, second refraction. The third will be once again it will be reflected from the mirror and the light ray will fall once again on the lens. Hence, we have to include the third term, which is the power of the lens. Hence, you get the power expression as P is equal to PL plus PM plus PL. That is 2 times the refraction is happening in the lens and 1 time it is happening in the mirror. So only we are including these 3 terms. Hence the power expression becomes P is equal to P1 plus PM plus PL. We know the relation between power and the focal length, which is P is equal to 1 by F. So here we are substituting PL is equal to 1 by FL plus PM is equal to 1 by FM plus PL is equal to 1 by FL. Since the focus of the mirror is infinity, Fm is infinity. Hence 1 by Fm, which is 1 by infinity, is equal to 0. We know that 1 by infinity is equal to 0. Hence 1 by Fm value will be 0. Hence the power is equal to 2 by FL. So, the total power of a plano-convex lens is minus 1 by Fm is equal to 2 by FL. Why we are having the combination as Fm? When you consider a combination of plano-convex lens, it acts as a mirror only. Hence, we have the total combination as minus 1 by Fm. The power we are considering it as minus 1 by Fm since the combination of lens and mirror will act as a mirror only. Hence, we are using the total power as mirror power only. So, minus 1 by Fm is equal to 2 by FL. Now, we know that minus 1 by Fm is equal to 2 by FL. Here we substitute the FL value which is given as 15. Hence, minus 1 by Fm is equal to 2 by 15. This we are going to substitute in our equation. 1 by F is equal to 1 by V plus 1 by U. Now, substituting the given data F and you get the equation as minus 2 by 15 is equal to 1 by V minus 1 by 20. Now rearranging the terms, we get 1 by V is equal to 1 by 20 minus 2 by 15. Further simplification, we take 1 by 5 as common. You can take it as common or else as it is you can find the LCM. It is up to you. Now I have taken 1 by 5 as common outside. Hence inside the bracket it will be 1 by 4 minus 2 by 3. Now inside once again you have to take LCM and you will get 1 by V is equal to 1 by 5 into 3 minus 8 divided by 12. Hence the answer is 1 by V is equal to 1 by 5 into minus 5 by 12. which is equal to 12 because 5 and 5 will get cancelled. So the image distance is equal to 12 centimeter. The 10th problem, find the ratio of intensities of lights with wavelengths 500 nanometer and 300 nanometer which undergo Rayleigh scattering. We know the Rayleigh scattering formula where intensity is inversely proportional to the fourth power of wavelength. Hence I is inversely proportional to 1 by lambda power 4. Here two wavelengths are given. So I am naming lambda 1 as 500 nanometer, lambda 2 as 300 nanometer. We know that I1 is proportional to 1 by lambda 1 power 4. Similarly, I2 is proportional to 1 by lambda 2 power 4. Hence, I1, substituting lambda 1, lambda 2 values, we get I1 is directly proportional to 1 divided by 500 nm whole power 4. I2 is proportional to 1 by 300 nm power 4. Now we are finding the ratio of I1 divided by I2. Hence I1 divided by I2 is equal to 300 nm whole power 4 divided by 500 nm whole power 4. Now you can cancel nm in the numerator and denominator, and the two zeros also you can cancel. Hence I1 divided by I2 is equal to 3 power 4 divided by 5 power 4, which is equal to 81 by 625. Hence the ratio of intensity I1 divided by I2 is equal to 81 divided by 625.